All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1206. Let's see here. Let's jump in here. All right, so I left you with a couple problems to do last time. Let's recap on what we did last time, because we covered a lot, surprisingly. I proved a lot of things, but there were a lot of things that were computational. So they actually gave us a lot of bang for our buck. So every single thing that I proved, we could use it in so many ways with so many different problems. So of course, we started the day with going over the definition of the derivative and finding derivatives using the definition. It's a very important type of problem. I'm definitely going to ask you how to do this. So you should know how to do this. And of course, algebra is going to come in handy here, because once you actually start plugging into this formula, f prime of x equals to the limit of, as h approaches 0 of f of x plus h minus f of x all over h, you're going to get something that you have to know how to simplify, and it can look various ways. It can have radicals in it, it can have squares in it, it can have a bunch of things in it, and you'll have to know the quickest way to simplify, ultimately to get to the point where you can plug in h equals 0 and get to the answer. Now that you know how to find derivatives with a much quicker method, just using these formulas that I derived last time, you'll actually be able to check your answer here. So you would be able to know, oh, I could write this as x to the minus 1 and do the power rule, and the answer should be minus x to the minus 2, and you'll get that, oh, that makes sense. I actually did the right thing. So you'd actually be able to check your answer, but actually being able to go through this method is something that I'm going to be testing for specifically. So we derived a bunch of formulas. At first, we found what is the derivative of x squared, of a constant times x, of 1 over x, of sine of x. I gave you the cosine of x for free. We spoke about properties of derivatives. We can factor constants in and out. Essentially, if you have a constant times a function and you want to differentiate it, you leave the constant alone, differentiate the function part. We learned that derivatives actually distribute across sums. So if you want to take the derivative of a sum of terms, you can just differentiate each of them individually. And we learned about the chain rule, super important. It's when you want to differentiate a composite function, which is when you have one function plugged inside of another function. So the input variable is not just x. The input variable is the output of some other function. So it's not just, oh, f of x. It's like f of g of x. There's like, instead of x, there's like a whole function inside, right? So it's not like just, oh, what's the derivative of sine of x? It's like, what is the derivative of sine of some whole function like x squared plus radical x minus 5 or whatever. So the chain rule helps us do that. And how it does that is you can differentiate the outer function and multiply by a derivative of the inner function. And of course, in the first case, when you differentiate the outer function, as you can see here, you leave the inner function intact. Students often try to just differentiate everything all at once. They differentiate the outer function and the inner function. This is incorrect. Differentiate the outer function, you leave the inner function alone, so this stays as g of x, and then you differentiate the outer, you multiply by the derivative of the inner function. So that's the chain rule. Did an example here. So it's like we had sine of something. This is plugged inside the sine function. So the sine is the outside function. So you differentiate the outside to get the cosine, and then you multiply by the derivative of the inside. And of course, you leave the original inside alone in the first part. Okay. We also saw that once we know the chain rule, we can actually generalize our formulas. So every time I gave you a new formula, I also gave you a chain rule version. I would recommend, if you want to memorize only one set of formulas, I would memorize the chain rule version set, because that also includes the basic set. Because pretty much if you apply the chain rule when you don't have to, the worst thing that happens is you multiply by 1, right? Because your u prime would just be 1 if your u is actually just x. So that's nice. We also learned how to differentiate the exponential function. We literally derived that from the definition. The derivative of a to the x is a to the x ln a whenever a is larger than 1. So just remember that a is larger than 1 here. It can work, of course, for a is less than 1. You just rewrite the function, right? So you can just write it to the minus x or something. We saw that e to the x is a special case because of the ln in this formula. Ln of e is 1, so the derivative of e to the x is e to the x. So e to the x and a constant times e to the x, that is the only function other than, that is the only kind of function other than the zero function that is its own derivative. So that's pretty special, pretty neat. And of course, here are the chain rule versions. More specifically, you kind of want to know this. The derivative of e to something is the derivative of the power times the original function. Very nice formula, very good to know. We then derived the derivative of the natural log, which we saw was 1 over x. In other words, the derivative of ln u is u prime over u, where u is the thing plugged inside the ln. So if something is inside the ln, you can just take the derivative of that thing over the thing itself, and that's your derivative. And what else did we do? Saw the derivative of ln of absolute value of x is also 1 over x. We use that right away right here, but it's actually going to come up later in the semester in like a week and a half, which is like almost half of a regular semester. But in the summer, it's going to be like in a week and change. We looked at the power rule, very famous rule. This is like when people do calculus and you see them years later and they never they just happen to not use calculus in their everyday life and they forgot almost everything. Like this is the one thing that everyone remembers, the power rule. It's just so for some reason it's very near and dear to people's hearts. The derivative of x to the n is n x to the n minus 1. They know, oh, you just bring that down and subtract 1 from the power. That's like one of the easiest things, and it's a nice formula. But it teaches you how to differentiate x to a power. So that was cool. We actually use that rule to derive a lot of the rules that we did previously. So you can actually use the power rule to figure out the derivative of a constant was 0, the derivative of x was 2x, the derivative of radical x was 1 over 2 radical x. Derivative of 1 over x is 1 or minus 1 over x squared. You can use the power rule to derive all of that. We also learn how to differentiate general logarithms by using the change of base formula. So that's rule 5 in the logarithm laws of logarithms that I gave you guys on the first day. And of course, there's the chain rule version. And we did some exam. Now, we also found how to differentiate a product. We realized that if you have two functions multiplying each other and you want to differentiate that, you can't just differentiate each piece. That would actually be incorrect. There's a whole formula you have to go through, which we derived from the definition, called the product rule. So when you have a product of functions, there's a whole product rule that you have to go through to differentiate those functions. So if you have a product and you're differentiating it, don't differentiate each piece. Rookie mistake. You need a product rule, and that's the rule. You differentiate one at a time and add them together. And by the way, the product rule does generalize nicely. I could even mention that right here. It's just a nice aside, I would say. By the way, the product rule generalizes very nicely. It's nicely a word. In the sense that there's a very straightforward way to think about it, in the sense that to differentiate a product, sum the product over and over and let each factor be the, I don't know, it's kind of weird to say it in words. Differentiate a product, I would say each function gets to be the derivative once and one at a time. Then sum all products. Now I am pretty sure that's confusing, so let me show you an example. So one way you can look at the product rule in the way that I gave it to you is that you have a product of two functions and each function gets to be the derivative once. So in one go, f gets to be the derivative, and in the second go, g gets to be the derivative, and then you add them up. Turns out the same sort of pattern would work with more functions. So if I have 3, it turns out that your product rule is going to have 3 terms where each function gets to be the derivative once. So the f gets to be the derivative in the first case, the g gets to be the derivative in the second case, and the h gets to be the derivative in the third case, right? And if you want to do the product rule of f, g, h, I, it's the same thing. F gets to be the derivative. Then g gets to be the derivative. Then h gets to be the derivative. Then I gets to be a derivative, right? Which is very nice that it actually works out that way. You can prove this by just using the product rule 2 at a time. So if you have like a derivative of fgh, you just think of f and g as one function and h as a second function, apply the old product rule, and when you simplify it, you'd realize you get this, and so on and so forth. So yeah, that's product rule is very nice in that way. You can generalize it to longer products very easily. I don't know of such a formula for the quotient rule, which is another thing that we derived. That tells us how to differentiate a division of functions. And really, it's like a repurposing of the product rule. We saw that. We use the product rule with the chain rule to derive this formula, but this is how you want to differentiate divisions. And we use that to find the derivative of things like tangent of x, which we could write as a division, sine over cosine. We use the chain rule to differentiate secant of x. And I told you about the derivatives of the other trig functions. And then we went into just applying these rules to a bunch of examples. And we're going to do a lot more of that today. So I think we're in, at least for me, in a very fun section where we're just going to be like killing problems, like just decimating problems left and right. We're not going to be talking too much about theory for most of this class, if not all of it. It's just going to be about, here's how you do this problem. Here's how you do this problem. Here's another formula. Let's kill a bunch of problems. That's what we're going to do, which is, it's nice not to be always existential and be like, what does it all mean? You can just like solve problems. So we're going to be doing a lot of that. And it's just a matter of applying the rules that I gave before. And I'm giving some tips along the way whenever they come up. So it turns out that the quotient rule and the product rule are not like the chain rule. There are, I wouldn't say, there are many instances where you don't have to use them, even though technically you can. And usually that's when one of the factors is a constant. So if you have f times g, and like maybe f is a constant, you don't need the product rule because you already have the constant factor. You just leave the constant alone, differentiate the function. If you have f divided by g and your g is a constant, then you don't need to do the quotient rule either. You just differentiate the f. And if you have f divided by g and your f is a constant, then what I would do is take the g, move it up to the -1 power, and then just do like the chain rule or some other rule. So there are times when you just don't have to do the product or quotient rule because they're overkill, and you would just rewrite them essentially and do it another way. And that could actually save you a lot of headache. So there are bad times to use the product and quotient rule, even though technically you can. But the chain rule is nice. Like you could literally always do the chain rule and you won't have a problem. Worst case scenario, you just multiply by 1, but then nothing else changes. But the product rule and quotient rule, you kind of have to be very careful. And we'll actually see some examples of that, I think, where we're going to want to be able to rewrite something so we don't have to use the product or the quotient rule, because they can be annoying if the functions get complicated enough. So yes, we did that. We did that. Of course, we need to know how to simplify things like factor things. So I gave a couple of examples where we had to do that, like factoring a very long expression by pulling out common terms, where we had to simplify a division, again, by starting to pull out common terms and factor the top and the bottom so we can cancel common terms. That's going to be important later. And then I left a bunch of stuff for you to try. Try the rest. Try these guys. Whew. Okay, so that's where we are now. Okay, so let's get through this. So trying this. All right, who tried this? What did you do here? Anyone tried this? Okay, so with a problem like this, I would also have some quick tips. So if you are differentiating a function or a log function, apply the log rules to simplify first. I mean, that's actually probably a general tip, I would say. General tip, actually. Simplify before taking derivatives. Impossible. And I guess you could also think of that as a kind of larger way to approach things. You tend to want to apply lower level rules and strategies before you go higher. So whenever you learn a bunch of rules at different levels, you kind of want to first try to apply the easiest ones at the easiest levels first. So you learn a bunch of rules in algebra, you kind of always want to do the algebra rules to kind of fix things before doing the calculus rules. Or even within algebra, there are times when you want to use lower level rules. So for example, if someone wanted to factor x to the 6 minus y to the 6, it turns out that there are two rules that would come in handy for that: the difference of squares and the difference of cubes and the sum of cubes. And you can actually do either one first. You can start with a difference of squares and then go to a difference of cubes, or you can start with the difference of cubes and then go use the difference of squares. But it turns out that starting with the difference of squares would end up getting you to factor easier than starting with the difference of cubes formula. It's actually a word. If you try it, you'll see what I mean. But actually applying the difference of squares formula before applying the difference of cubes formula actually makes a huge amount of difference. And that's just at algebra level. Calculus level is the same thing. You kind of want to simplify things with and apply lower level rules first. Now, whenever you see a logarithm, turns out, remember, logarithms have a lot of nice properties and a lot of nice simplification properties. They can turn powers into multiples. They can turn multiplication into addition. They can turn division into subtraction. They can do a lot of things, right? So you tend to want to take advantage of that. In fact, there are going to be times where you don't have a logarithm there, and we're literally going to put one in order to make it easier. So we're going to do that a little bit later. That's called log differentiation. So whenever there's a log there, take advantage of it. A lot of students while not incorrect, many students will get stuck or incorrectly or incorrectly compute a derivative like this. By immediately going to the ddx of ln u is u prime over u rule. So if we had ln of, what do we have here? 2x plus 1 to the 8 over x squared plus 1 to the 5th. Right? A lot of students will be like, all right, well, this is like a u, isn't it? And they'll just immediately go into, okay, I'm going to do the u prime over u. And so they're going to be like, all right, so I need to just put the u down here, 2x plus 1 to the 8th over x squared plus 1 to the 5th, which of course they're going to flip that and multiply. And then on top, what we will do is we're going to find the derivative of 2x plus 1 to the 8th and x squared plus 1 to the 5th, right? But remember what we had. Remember what we went through in order to do this. Remember what it took to do this? Right? We actually did that yesterday. Yeah, that was this guy, right? So imagine doing all of this in the numerator of that thing that we just had, right? Just to get that one derivative, I'm going to do all of this and then divide it by the thing itself, which then I'm going to have to flip and multiply and then simplify some more, right? You don't want to do this if you don't have to. Is what I'm trying to say. So yeah, not the way to go, just directly applying the calculus rule, because you have log rules. You want to use the log rules first. And you're going to see the difference here. It's better to use the log rules first. And here's the difference. So you have 2x plus 1 to the 8th and x squared plus 1 to the 5th, right? And instead of just trying to differentiate that, I'm actually going to simplify it. And how can that simplify? Well, it's log of a division. So I can actually change that into a subtraction of logarithms. And then I have the powers on top. So each of those powers, the 8 and the 5, would go down in front of their respective logarithms. So this is actually the same as 8 ln 2x plus 1 minus 5 ln x squared plus 1. And you have just saved yourself the trouble of doing the quotient rule with the chain rule inside of it, and then having to factor and simplify all of that stuff. This is way easier, right? So now the derivative, we just take the derivative of the sum is just the sum of the derivatives, right? So this one, we can apply u prime over u to it. And this one, we can apply u prime over u to that. And it's going to be much easier to get those answers now. So here I have the 8 times u prime over u minus the 5 times u prime over u, right? It's going to be 16 over 2x plus 1 minus 10x over x squared plus 1. And that's the answer. Now, look how easy that was compared to that, right? It's not even close, right? Like this is way harder to do this, right? Like if you have a logarithm, apply the log rules first. And for whatever reason, every semester I say this whenever I teach this class, and every semester I have students not doing this. Like I put a problem on the test specifically to test this, where I put logarithm of something very complicated, and you'll see it on the practice test that I did that. Put logarithm of something very complicated, and I'm not expecting anyone to do u prime over u because I spoke for like 5 minutes talking and explaining the benefits of not jumping into that. And I still have students trying it, and then they end up either getting stuck on the problem or getting it wrong. And it's like, even if you get it right, you're still losing because you're going to spend so much time getting it right that you're going to run out of time on other stuff. It's like, no, there's a logarithm, use the log rules, right? So if you have logarithm of something complicated and you're going to do calculus, use the log rules. So, and I did mention this, I think, way back. Maybe it was the second lecture. It's a throwback. I'm sure I mentioned it somewhere. Yeah, like here. Expanding logs is important when you want to apply calculus rules, right? Like I told you way back then. Like if you're going to do calculus, you want to expand a logarithm before doing calculus. And I also mentioned combining them is easier for doing algebra stuff. So if you want to solve an equation, you combine the logarithms. If you're going to do calculus, you expand the logarithm. You never go into just a single logarithm with something complicated to do calculus. You don't want to do that. You expand the logarithm whenever you want to do calculus with it. Always, every time. Otherwise, it's not like you're going to get it wrong per se, but the chances of you getting it wrong are much higher. And even the best case scenario where you do get it right, you're going to spend so much more time than you had to. Like the problem is easy And by not applying the log rules, you're going to make it hard, right? So just a pro tip there. Apply the log rules before you want to do any calculus with a logarithm. You always want to expand logarithms before doing any calculus. You only combine logarithms if you want to solve equations or do some algebra stuff with it, because then you can just raise both sides to the base and then you get rid of the logarithm. And having all the logarithms in one spot makes that easier. Okay. So I spent a long time to explain all that, but students always just ignore it for whatever reason. And it makes their lives so much harder when they ignore it. I guess that's true with a lot of things. Here's another one. Did we get this one? Oh, that's, remind me, let me do the notes thing again. Okay, so I've pasted the link to the notes in the chat again. So this one, is this easier? Anyone try this? So what do we do? The product rule? How do we differentiate this? What's the derivative of that? Anyone?
Is it e to the radical 2 plus 1 over 2 radical e to the radical 2 plus 1?
You're talking about e to the radical 2 thing? E to the radical 2? The derivative of that is what?
It's 1 over 2 radical e.
1 over 2 radical e, like that?
I'm not sure how to find the derivative of e.
You mean an exponential function?
Oh, is it
there's
like
a
ln? Is it ln x?
Are you referring to this d dx of e to the u is u prime e to the u?
I think so.
Or you just the derivative of power times the original function? Or you don't do anything to the power with the exponential. But you're already thinking too hard here. What kind of thing is this? Or in fact, this? Is it an exponential function? Is it a polynomial? Is it, what is it? Maybe I'll give you a hint. Does it have x's in it?
Is it a constant?
It's a constant because there are no x's, right? X is your variable. There are no x's here. It's a constant. How do you differentiate a constant?
Is it 0?
It's just 0. Derivative of a constant is 0. Doesn't matter what the constant looks like. So yeah, you actually don't have to worry about the derivative at the first part at all because it's actually a constant. So here I have essentially a constant times x cubed. How do we differentiate a constant times x cubed?
do we just use the power rule? So is it like just 3x squared?
Right. So we have the constant factor rule, which says you leave the constant alone and you differentiate the function, right? So it's that. Okay. So yeah, watch out for the rules. The rules will tell you what to do, and the rules are very dependent on the type of thing that you're looking at. So where are we? So where are we? Yeah, so we had the chain rule, but notice that we had the exponential rule. It should not be lost on you that there's an x here and there's an x there, like it's a function, right? It's not the same thing all the time. It changes as x changes, right? So this rule applies in that situation. Here again, when you have e, there's an x here, there's an x here. That should not be lost on you. Whenever there's a logarithm, like there's an x in it, right here, right? So it's not just log of a constant, which would be a constant. And we always have, and, the power rule, right? There's an x here and there's a number here, right? And notice that that is very different from the exponential rule, where the number is here and the variable is here, right? It's a different when the variable is on the base and the number is in the power than when the number is on the base and the variable is in the power. One is an exponential, which you apply the exponential rule. One is a power function, which you apply the power rule. So all these rules are very important that you pay attention to what they're actually applying to, and when there are x's in it versus not. And then there's this rule for constants. Derivative of any constant is 0. How do you know it's a constant? There are no x's in it, right? There's nothing that's changing, right? So there's no part of that thing that is moving around, right? So that tells you that it's a constant. So you see this, it looks complicated, but it's there to fake you out. It's not complicated at all. It's literally as easy as differentiating x cubed, because you can literally ignore the other guy. Just leave him alone because he's a constant. What about this one? Mention here, sine x squared means sine of x squared. Like when there's just like one thing inside the sine function, sometimes we don't put the parentheses around it. We would put parentheses around, like if there's a bunch of things in there, like a sum or something. So that's what we have. So how do we do this here? You'd realize that the sine function is an outside function and the x squared is an inside function. So chain rule is what applies here. So this would be the derivative of the outside, leave the inside alone, multiplied by the derivative of the inside, which, I mean, we tend to like to write it the other way. Now, when you look at this one, it looks very similar to the untrained eye, but it's actually very different. You see when the square is beside the x, versus when the square is beside the cosine, they actually mean very different things. A square beside the cosine actually means the entire cosine of x is squared, not that the x by itself is squared, right? So as I was mentioning before, these are the little things where it just causes a lot of headache in the sense that students not paying attention to notation, like where the square occurs, matters a lot. So when I spoke about not being sloppy and forgetting your parentheses or doing this or doing that or not writing things down properly, it's not just me being a stickler. It literally actually affects your performance in mathematics, and it affects how well you can do it. Because when you read something and you don't even understand the question, essentially, how are you expecting to get the right answer all the time if you're not even being able to read and understand the question? So it needs to come down to notation is a lot of it, actually. So I can tell you for sure, students would mix these up all the time. Like students will mix up what it means to be sine of x squared versus sine squared x. They're actually very different. And students will treat them as the same sometimes, or sometimes they'll literally treat them like they're the other person. And yeah, you don't want that. You need to know the difference between the two. Versus sine squared x, which means sine of x all squared. And they're different. How do you know they're different? Because in this one, the x squared is the inside function, whereas in this one, the entire sine function is the inside function, right? You have a very different inside function. So when you're applying the chain rule, it makes all the difference in the world. So again, this is applying the chain rule, but the chain rule is being applied with the cosine being the inside and the square being the outside, as opposed to the cosine being the outside and the square being the inside. So again, it's the chain rule here. But it's applied very differently. The square is the outer function, so now I'm going to bring the 2 down and subtract 1 from the power. So this is just cosine to the 1 power. Then I'm going to multiply by the derivative of the inside, which is the derivative of cosine. So it's minus sine of x. So this is minus 2 cosine x sine x. Or minus sine 2x, actually. Right? So these two problems here, not super difficult, provided that you're paying attention to notation. And this one here as well, it's not difficult, provided you're paying attention to notation. So yeah, these are the kind of problems where it's students will get into a lot of trouble just because they're not reading correctly. And so, yeah. And it's interesting. And this, the log problem is another one too, where students, they read it correctly, but they just have a very inefficient way of approaching it. And so there are times when, I mean, it's funny, but well, it's funny to me. I guess it's not funny to the students, but there's sometimes when the students are like, oh man, Jhevon, that test was too long, bro, man. How do you expect us to finish that? And I'm like, what are you talking about? I gave you a bunch of one-liners. And they're like, what are you talking about? I took a whole page to do all those problems. I'm like, you're not supposed to. Like, you weren't supposed to. You're totally misreading everything. I really didn't want to make it hard. I really put like some easy problems you could get in a couple of lines. But because they didn't read it correctly, or because they tried to apply the more high level rules before they applied the more basic rules, it just ends up turning into a mess. So yeah, pay attention to notation. It's not just something that people mess with you about, like your math teachers, right? So like there are times when like I would when I'm grading students and they like make a mistake with like a sign or parentheses or something, I'd take points off, and they're like, "Oh, come on, professor, you know I meant to put it there," blah blah blah. I'm like, dude, you don't understand. Like, there's going to come a point in your life where being sloppy with that is really going to hurt you. So I need to let you know it's not okay. Yeah. So, all right. Moving on to this one, which is a very interesting problem. I even stated it differently than I stated all of these. If f of x is the absolute value of x, compute f prime of 0. Now, there are a couple ways to actually go about this. First, I'm going to do it by the definition because I wanted to, like, again, another throwback, just point out to another limit that we've done before. So here, by definition, one way, by definition, f prime of a would be the limit as h approaches 0, f of a plus h minus f of a all over h. Here, h is just some constant that we're plugging in for x. Okay. So essentially, what that would mean is f prime of 0 is going to be the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h, which of course is just f of h minus f of 0 all over h. Now, if our f is the absolute value function, which it is, because that's what I said it was here, then this is just going to be absolute value of h minus absolute value of 0 all over h. Now, absolute value of 0 is just 0, so I can pretty much ignore that guy. I would have the limit as h approaches 0 of absolute value of h over h. Now, this guy, on one hand, we did it very recently, but on the other hand, in a regular semester, we would have done this weeks ago. So we covered this maybe 2 lectures ago or something like that, maybe 3. But we actually looked at a limit where I used x instead of absolute value x over x. And we saw that this does not exist. And that was because on the right side of 0, it was 1. And on the left side of 0, it was minus 1. Because absolute value of x gives you x when x is greater than 0, so it simplifies to positive 1. And absolute value of x gives you negative x when x is less than 0, so it's simplified to negative 1. And the two sides didn't agree. So here, actually, the answer is does not exist. It turns out that this derivative does not exist at this point. It exists at other points. So if I plugged in any point that was greater than 0, the answer would be 1. If I plugged in any point that was less than 0, the answer would be negative 1. But at 0 specifically, it doesn't exist because the derivative is essentially behaving like this function that is discontinuous at 0. So yeah, so that was a nice, not nice, instructive. It's actually one of the quintessential examples to talk about where derivatives don't exist. So derivatives are very powerful. I told you they solve the rate problem and we can do a lot of things with them, but they're not all powerful and we can't always take a derivative. And even if we can take derivatives, we can't always take the derivative of any function at any point. There are times where a function will misbehave at certain points and we can't take a derivative here, but we can take it over there, right? And so derivatives don't always work out. You can't always do them. And this is one of the functions that is always used as an example because it's a function that's continuous everywhere, but not differentiable everywhere. You can't actually find the derivative everywhere. Specifically at 0, you will not be able to find a derivative. I would say another way This will be method 2. Using formulas. So if my f of x equals the absolute value of x, that would mean that my f of x is equal to, well, x if x is positive, 0 if x is 0, and minus x if x is negative, which means that my f prime of x is going to be 1 here, minus 1 there. Which these guys kind of indicate to you that that part is not going to actually work out. Because immediately to the right of x, you're 1, and then immediately to the left, you're negative 1. You're not going to be anything at 0 itself. Well, not technically. You'd have to actually examine the limit, because there's a division by 0 that happens, and that's why it's a problem. These indicate this. That it does not. Say that it may not work at x equals 0. The limit definition will confirm. And so you'll realize that f prime at 0 just does not exist, because like immediately to the left and to the right, you're not going to work out. But this way is a little bit tricky if you did it directly, because you can't really know for sure that the mill is going to work out. You could like have the hole filled in or something, and you'd have to kind of check for it. But yeah, this is by the limits, which starts to raise an interesting point, which is the existence of the derivative. Let's actually talk about that. It turns out that there are some situations in which you can know when the derivative exists versus not. It's actually nicer to talk about where it does not exist. So I can tell you about where it exists, but it's actually not going to be probably as useful as you would think. Let's say here. So remember, recall the derivative gives the slope of the tangent line that approximates a curve at a point. This would kind of suggest, and this is the truth, that f of x is differentiable at a point if it is approximately linear there. And what does that mean? It means when you zoom in, it starts to look like a straight line. It starts to flatten out into a line, and that's why we can say, oh, let's pretend it becomes this line, and then let's find the slope of that line. But if you start to zoom into f of x, and it doesn't start to look like a line, then what are we actually doing now? Like how are we getting a straight line here? Like you won't like have a line to do. So this kind of suggests where derivatives won't work. But for us, it's going to work at, it's going to not work at very few cases. It's going to be 3 cases, in fact, where derivatives do not exist. So this is even a question where I can ask you literally on a picture, like a graph, like I can say, oh, point out the points on this graph where you can't find a derivative, right? You should actually be able to spot them. And the idea is it's going to happen at spots where if you zoom in, you can't really find a straight line to describe the function. And one way is at sharp corners or cusps. So like if your function looks like this, that, or something like that, or like this, or that, right? Then the derivative doesn't exist here. The derivative won't exist at those red points. Intuitively, the reason is if we keep zooming in on a sharp corner, it's never going to flatten out. It's a sharp corner, right? It's never going to look flat. It's sharp, right? So it literally comes in at an edge like this. No matter how much you zoom in, it's never going to look like a line. So you can actually take derivatives there. And if you actually try to take a derivative there and you apply the definition or some other formula, you're going to realize that it's not quite working out. So that's why example for f of x equals the absolute value of x, we know that this guy looks like this function. And the derivative won't exist at 0 specifically because there's a sharp corner. But otherwise, absolute value of x is a function that behaves itself. It's continuous everywhere. It's continuous for all real x. You'll always be able to plug in an x value and get an answer. But you can't always find a derivative. You can find a derivative to the right, right? What is the tangent line to a point on the right? Well, it's literally the function itself, because the best line to approximate a straight line is the straight line itself. So the slope of the derivative is going to be 1 because that's the slope of the line on this side. Same thing over here. At any point, the line itself is its own tangent line. So the slope of the tangent line is the slope of the line itself, which in this case is -1. So on either side of 0, we can find a derivative, but at 0 itself, we cannot because it's a sharp corner. And no matter how much you zoom into a sharp corner, it's never going to look like a straight line. You're not going to be able to approximate it with a straight line. A second point is where f of x is not continuous. So if you have like a function that's there's a hole or there's a jump, right? Then derivative does not exist here. Doesn't exist here either. Why? It's a hole. No matter how much you zoom in on a hole, it's a hole. It's never going to look like a straight line. It's a gap. It's always going to be a gap, right? Similar with a jump. You'll never make a gap in a function look like a straight line. You can't do it. There is no there's no function there to attach a line to and measure it. So where f is not continuous, you'll also not have derivatives existing. The third case is is even different from those. It's a little bit hard to see on a graph, but you could see it on a graph if the graph is like high enough resolution, or the graph is described in terms of the formulas that make it up, and you'll be able to figure it out that way. And this is where a function has a vertical tangent line. Now, there are two kind of ways in which this doesn't exist. For one, yeah, it's hard to actually put a line at a single point and kind of turn a point into a line. But on the other hand, we also know that vertical lines don't have slopes, right? The slope is undefined for vertical lines. So there are two reasons why you can see this doesn't work. But this is the behavior of some functions, that they can go vertical for like a split second. So they have a point where they're almost vertical when they hit that point, and then they switch after that point. And so like the tangent line, the best fit line would be like a vertical line going through that point, because they're approaching vertical before it, and then they leave vertical right after it. So the function goes vertical for a single point. And derivative doesn't exist there. And yeah, now of course, a function can never go vertical for more than a single point, because it would fail the vertical line test and it would no longer even be a function. So it only can do this for like 1 point, a split second. It's approaching vertical, not quite vertical, it's getting steeper, super steep, but it never actually goes vertical for more than a point before it starts to get less steep. So that's a situation in which a derivative won't exist either. So there are three main situations in which derivatives won't exist: where a function is not continuous, where you have sharp corners, and where your function goes vertical for a single point. So you have like a vertical tangent line. And yeah, absolute value of x is the typical example that's used to introduce this notion, which shows you that, hey, this function is a very nice function. We use it all the time, but we can't differentiate it whenever we want. So yeah. Okay. We did all those examples. We talked about the existence of a derivative. Let's talk about more derivative stuff, like more like computational stuff. So this one is also going to be, I think, a little bit weird to wrap your head around, but I think if you start to think about it in the right way, it shouldn't be, because at the end of the day, it's really just an application of the chain rule. And so this is a topic called implicit differentiation. And so this is differentiating implicitly defined functions, which might be a strange notion to some of you. So let me actually tell you what I mean. This guy's used to differentiate implicitly defined functions. What are explicitly defined functions? Functions can be defined in two main ways. One is explicitly. And this means the function is written in this form, like y equals f of x. So you have your dependent variable isolated on one side of the equation, right? So okay. Which is almost every function you've seen up to this point, right? Y equals, example, like y equals x squared, y equals x plus 1 over x plus 2, y equals e to the x minus ln x squared, etc. A lot of stuff. Like once you have y equals and there are no y's on the other side, it's a function and it's explicitly defined. And we know how to deal with these already. But there's another way to define functions, and this is called implicit, to define a function implicitly. So this is when you don't have the dependent variable isolated on one side. It's like you would have a function of two variables equals a constant. So independent and dependent variable mixed together. I don't know how else to say it, mixed together. Right? So you don't have the y just isolated very nicely, explicitly out in the open on one side. You have your x's and y's kind of mixed up. So example, it's like xy squared minus 3 ln y plus 2x equals 4. Or you can have x squared plus y squared equals 1. Or yeah, x, y over e to the y plus x equals 2 or whatever, right? So here you don't have your y isolated. Your y is still some function, but you really don't know what it is. So for example, here we could say, well, I could solve for y and I could get plus or minus the radical of 1 minus x squared. And that's writing it explicitly, but then you'd have to choose what side you want. Do I want the positive side or the negative side? But sometimes you can't solve for y. Like here, y equals, I don't know, like what you expect me to solve that? Here, y equals, come on, man, cut me a break, right? I don't know what y equals in those cases. So this presents a challenge because there are times when we have implicitly defined functions and we still want to be able to do calculus. We still want to be able to differentiate stuff, right? And we still want to be able to differentiate with respect to the dependent variable, the independent variable, right? We still want to think of one guy as an x and another guy like as a y. One guy is the input, the other guy is the output, and we want to know how fast is the output changing in relation to the input. And so we want to differentiate with respect to the input, right? And we want the other guy to respond. So that's still a thing that we care about. It's still a thing that we might need to do. The question is, how do we do it, right? Because all the formulas that I gave you for derivatives so far only had x's in it. Like you had x to the n, right? Like y equals x to the n, then y prime is in x to the n minus 1, right? So how do the formulas work when there are y's mixed in, right? That's the question. So how do we differentiate in the implicit case? And the answer is chain rule. See, the nice thing about the chain rule is the chain rule already knows how to deal with functions that are mixed together, right? So there's like a f of g of x. Like there's this g of x that's in there, that it's not just an x, it's not just the independent variable. It's already something like mixed up. The independent variable is like mixed up with other things. So it kind of knows how to deal with that already. It's a very important piece of machinery. I told you the chain rule is important. It helps us in a lot of cases. So to illustrate, I'm going to give you a bunch of examples where I want you to differentiate them using the chain rule, and then I'm going to show you what is the equivalent in the kind of like implicit world, right? So let's say here I want to differentiate. Oh, I heard something on the computer. Let's say here I wanted to differentiate some function f of x. What would that give me? Or I wanted to differentiate x times some function, right? Or I wanted to differentiate maybe x divided by some function. Or I wanted to differentiate ln of some function. Or I wanted to differentiate, say, x squared times some function squared, right? So let's go through all of these. And then I'm going to make a comparison at the end. So first one, derivative of f of x. Okay, so this is the hardest one, so you need to pay attention. The answer is going to be f prime. Okay, I need to drink after that one. That was harder than I thought it was going to be. All right, so that's the first one. Let's move on to the second one. In the second one, notice that I have a product of functions now. I have x times something. Now I don't know what that something is. So can we even differentiate it? Well, I know what the derivative would have to look like. It's a product, so I would do the product rule. So I would take the x, differentiate it, leave the function alone, plus leave the x, and differentiate the function. All right, cool. You don't really see where the chain rule is happening here, but technically it did. Technically there was a 1 that's happening here, but let's not worry about it too much. What about this one here? We might need some space. Now this one is a division, which we have the quotient rule for. So you can apply the quotient rule. So it's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay. So again, so far, you're probably not seeing where the chain rule is happening, but I just want you to get used to manipulating a derivative when you don't even really know what the function is that you're manipulating. Okay. Now in these two, you're going to start to see the chain rule more efficiently, right? Or more like explicitly. So we know that the chain rule told us Confucius that if I wanted to differentiate ln of u, the answer is u prime over u, right? The chain rule told us that, right? So this guy by the chain rule is going to be, well, f prime over f. Okay, all right. Let's get a little bit more complicated. This one. Let's make this a little bit more complicated. Let's make that a cube so you can see something. Now here's where you're going to see it in like full force, where you're going to, oh, I see the chain rule happening here. All right. So again, this is a product. So we're going to apply the product rule. You're going to want to differentiate that. So you're going to differentiate the first one, leave the second one, plus you're going to leave the first one and differentiate the second one. Now, how do you differentiate f of x all cubed? Well, you think of the f of x as an inside function and the cubed as an outside function. So you differentiate around it, you leave the inside alone, subtract the power, then you multiply by the derivative of the inside, right? So that's chain rule 101. You have an inside function and an outside function. That's how you do it. You differentiate the outer function, leave the inside function alone, then multiply by a derivative of the inside function. Okay. So we're just applying any questions on this so far, what I'm doing here? Okay. So now you might be wondering, why did I do all that? Because now I'm going to want to make a comparison. So below this, I'm going to want to make comparisons between something that's going to essentially be treated exactly the same way. Like I'm not doing anything at all different. Literally what I'm going to do is change notation. So here, instead of d dx of f, I'm going to write this as d dx of y, right? So I'm thinking of y as f of x, right? So here, we're thinking of y it's some inside function. Right? So whenever you see y, don't just think of it as y. Just think of it as, oh, this guy is some f of x. There's some function inside it that I don't know what it is. Just like right here with the f of x, I don't know what it is. Like what's inside of this? What's inside of this guy could be anything. There could be an exponential in there. It could be e to the x. It could also be x cubed minus 12. It could be ln of x over 17. Like I don't know what the f of x is, but I can still find an expression for the derivative just by applying the derivative rules at a higher level, right? So in the same way, if I had a y here, how would I differentiate the y? Well, y prime, of course, that's the derivative. Okay, now to compare to this one, this is like if I had the derivative of x times y. So here I have my x and y mixed up. They're in fact multiplying each other. How do I differentiate that? Well, product rule, of course, because they're multiplying each other. So you're going to take the derivative of the first one, leave the second, plus leave the first, differentiate the second. So that's going to be y plus xy prime, right? And nothing different is happening than what we did before. Exactly the same thing. It's just that instead of f of x, I'm writing y. So move over here. This is like, what if I had d dx of x divided by y? Well, how would I do that? Well, quotient rule, of course. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. That's the derivative. Nothing crazy happened. Okay. This guy here. This is like if I were to have d dx of ln of y instead of ln of f of x. What do? It's u prime over u, but your y is the u. Your y is this function. So it's just going to be y prime over y, just as how it was f prime over f. Now let's look at this one. This is like if I had d dx of x squared y cubed. So I want to differentiate this expression with respect to x. And the y, I'm just thinking of it as some inside function. It has x's in it, probably. So what I would do is, first of all, the product rule. So I'm going to differentiate the first function, leave the second, plus leave the first, differentiate the second. Now, how would you differentiate a y cubed? Now, students would tend to just apply the power rule and just say, oh, that's 3y squared. However, that would be incorrect because the y is an inside function, which means the chain rule demands you have to multiply by its derivative, which means I need to multiply by a y prime here. And the idea in a nutshell, although this becomes dangerous when you start to move further along, but the idea in a nutshell is if you're differentiating something with an x, you just do it as normal. If you're differentiating something with a y, multiply by y prime. That's essentially what it boils down to in this case. But that's only in the case where you only have two variables. It can get a little bit trickier later. Or if I switch variables. So the idea is, so the main idea when a function is explicitly, implicitly, I want to deal with, we already know how to deal with it, explicitly, implicitly. Defined. Don't want to go any wider than that. I'm writing lean again. If you put those lines back. Then when we differentiate an x term or the input variable, just do it as usual. When we differentiate a y term, the output variable, multiply by y prime derivative. And y, chain rule, is y. Because if you think of the y as some function in f of x, then whenever it occurs, it's occurring as some sort of inner function. You just don't know what it is. So whenever y is written, there's really some function hidden in there. And you can think of it as being hidden inside the y. And so the chain rule is going to say, whenever you differentiate that, you have to multiply by the derivative. Yeah, that's essentially the main idea. So students often forget to do the y primes when they should be doing it. Occasionally, not often, students will start to like throw in x primes for some reason, but the x prime is going to be 1 when the x is the independent variable, so you don't need to do that. Like when you're differentiating the x term, don't do anything. Like it's the x, it's the input. If you're differentiating the y term, by the way, let me also mention, in Leibniz notation, the dependent variable is indicated by the variable in the bottom. So when we write dy dx, this is another reason why Leibniz notation is actually a lot more functional. It's already telling you a lot of things just by writing down that notation. When I write dy dx, this is the derivative of y with respect to x. What it means is that x is thought of as the independent variable. The dependent variable. Oh, this is at the top. Should have wrote independent variable, but whatever. The independent variable is on the bottom. That's the guy, when you differentiate him, you don't need to do anything. If you differentiate anyone other than him, multiply by their derivative. Multiply by its derivative. And so this guy would be the dependent variable. Okay, so the Leibniz notation would actually indicate to you. So let's do an example. It's the first example in the new topic we're doing today. Find dy dx equals y prime for the following. A, xy equals 1. B, 5x squared plus 2xy plus x to the fourth y squared equals 4x cubed. See, x squared plus y to the 7 minus 2y equals 3. I think I had some more examples. The 4x squared plus 2xy minus 3x squared y squared plus 4 equals 7 minus ln x. E to the x plus y squared plus ln of x plus y equals 3. 2. Find dv dp if p plus 5 over v squared times v minus 0.03 is equal to 9.7. So those guys. So we're going to find the derivative of all of these guys. In fact, we're going to find y prime for all of these guys. Or in the second case, we're going to find a different prime in problem 2. But it's about that time we should take a break, so let's do that. So yeah, we'll take a 10-minute break and then we will come back and kill all these problems. So I will see you guys in 10 minutes.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Okay, we're back. So as we were asking, let me just take some time here. So test one, it's Friday, is that 11? 6/11 at 9 a.m. to Saturday, 6/12 at 9 a.m. You can log into Gradescope at any point during that window and start your test. The test itself will not be the whole time. I think it's going to be very similar to the tests that I have on the class website, the ones that I give on paper. And you're pretty much going to write out your answers and scan them and send them to me, or even better yet, as I said, log into Gradescope on your phone, and then you can literally take a picture and upload, just like press a button and upload from your phone. There'll be, like when you're viewing the test, there'll be like a button that says upload, and you can upload directly from your phone, just take a picture. And yeah, so the test, the length is usually going to be like an hour and 15 minutes long. I'll probably make yours an hour and a half long, give you an extra 15 minutes to upload. Maybe even an hour and 45 minutes just to be completely safe. But I'm going to write it so that you can do it in an hour and 15. Like I'm going to write it to be the same length that I would for a test, to be an hour and 15 minutes. But I'll give you a lot more time for like technical issues or uploading issues or something like that. Just put a little cushion in there. When you start the test, you will have at 1 hour, I'll say 45 minutes to complete it. So that is 1 hour, 15 minutes for the test, plus 30 minutes for uploading. And tech issues. If you lose connection, you can just log right back in. So if something happens and your computer froze or something, you can literally just restart your computer and get back in. So it'll leave it open for that entire window. So once you log in, the clock is going to start, and you will be able to access your exam over and over repeatedly during that 1 hour and 45 minutes. So if you need to take 5 minutes or 10 minutes to like restart your computer in the middle of the test, you're not really going to hurt much from it. You can log in and re-upload repeatedly during this time window. Yeah, so for practice, the practice tests on the class webpage are useful. So I would try a couple of those, maybe tonight, maybe even early tomorrow, see how you do. There's a practice test one, and then there's an actual test one that I gave my class in the past. You can go over them, and the solutions are there, so you can check your work after. And if you do well on those and you feel comfortable, you should be fine. The only other thing I see could potentially be on your test that wasn't on those would be stuff that I might, since it's a computer, it'd be easy for me to like copy and paste some pictures. So I might even paste some pictures and just ask you about, oh, where is this differentiable, or where is this blah, blah, blah. And if you want examples of questions like that, I would ask, you can check out the old quizzes as well. So on quizzes, I ask questions like that sometimes, where I put a picture on the quiz and identify where the function is not continuous, identify where it's differentiable, where it's not differentiable, identify blah, blah, blah. So also know how to answer limit and derivative questions from pictures. Yeah. So that's all I would say there. Yeah, I don't think there's anything else to say about that. So you have practice exams on the class webpage, and you have solutions with it, and you have like a 24-hour to log in and take your test. Once you log in, you'll have an hour and 45 minutes to finish it. But the test itself should really only take you about an hour and 15. And so you have a lot of extra time for like, you have to restart your computer, or you have to log back in or something, or, just upload. You have that. Yeah. And as always, the link to the class webpage is always pasted in the video description, as well as you guys should all have it. I gave you in the chat in the first day of class. And in the notes on the first day of class, I actually pasted the syllabus. Yes, so that link. So that's the class link right here. Okay, all right. Okay, let's get to this. Okay, so let's do this. So here's one. Find y prime. Remember, that's always gonna be the goal whenever we have the x's and y's here, because that's what the question asks for. Find y prime dy dx. So there's actually a couple ways we can do this. We could do this one. You can actually do this without implicit differentiation. You can actually solve for y, just like it's not a big deal to actually solve for y here. So we know here that x is not equal to 0. Otherwise, we'd have xy equals 0, right? If x was 0, that's what you'd have x times y equals 0. But you have x times y equals 1, which means that x is not 0, which means you can actually divide by it. So you can solve for the y, and you get 1 over x, and we actually know how to differentiate that. So y prime is just going to be minus 1 over x squared. So here we started out implicit. This is implicit. Since the x's and y's are mixed together, but it's we could turn it into an explicit right away. However, I want us to practice implicit differentiation, so I'll do it the implicit way. Okay, so how would it look like the implicit way? So x times y equals 1. So what you would do is first, you would differentiate both sides. With respect to x. Now, on the left side, you actually have a product of functions. You have x times y. Now, remember, we don't know what the y is, but it doesn't matter. We can still find the expression for the derivative. Differentiate the first one, leave the second, plus leave the first one, differentiate the second. All derivative rules apply. I should mention that. Because sometimes students are doing implicit differentiation and they they think just because it's an implicit differentiation, suddenly the product rule isn't a thing anymore. They can just throw that out the window. No, you have to obey all other derivative rules. Very important. So I'm talking about product rule, quotient rule, all that other stuff, chain rule, etc. Okay, so those are still a thing. All right, so don't forget that. So here I have x times y. It's a product. I need the product rule. So I'm going to differentiate the x, leave the y, plus leave the x, differentiate the y, which is y prime. Technically, you can think of this as the power rule. The derivative of y is 1, but because it's not the x, you have to multiply by y prime, so you really get 1 times y prime. So it's like a hidden chain rule going on. Derivative of 1 is, of course, 0, because that's a constant. So here we were applying the product rule. Okay, so you differentiate both sides, and now what you do is you solve for y prime, because that's what you want to find. You were asked to find y prime. So that just involves algebra, really. So, so this implies x times y prime equals minus y, which I can move over that there. And then my y prime would be minus y over x. And that's the actual answer. That's the answer. Now, while we're here, there are a couple things that we should deal with right off the bat. For one, the answers look different. And in here, which might be a little bit unsettling, there's a y in the answer on the other side, right? Which this whole time we've just been seeing y prime equals something with only x's on the other side. But here there's a y on the other side, which might cause you some concern. But I just want to assure you that there's nothing wrong with there being a y on the other side. If you're solving for something in an equation and you want to say what this thing is equal to, the only thing that matters is that that thing is not on both sides. I want to solve for y prime. As long as there's no other y prime on the other side, we're good. If there happens to be a y on the other side, it's okay. It might look weird, but it's okay. So I would say a couple of remarks here. One, the implicit version of the answer has a y in it. This is fine. Another meme opportunity, that the dog in the house that's burning down that says this is fine. I should put that here. Okay. I didn't know I would say it that way though. This is fine. And so that's just it. That's all I'm going to say about that. It's fine to have the y over there. Don't freak out. Second, the answers look different. I do want to assure you they're not. They're not though. And here's how you can know. So in the implicit case, we had y prime equals minus y over x. Now, the thing is, in this case, we actually know how to solve for y. Like we did it very easily right here. So if you realize, but we know how to solve for y, but we happen to know how to solve for y. We're not always going to know, but we happen to know how to solve for y. And so I'm going to plug that in. We know in this case that our y is actually 1 over x. You could just divide both sides by x. And so this is actually minus 1 over x squared. Keep, change, flip, right? Which is same answer as the same answer as the explicit case, right? That's what we got up here, minus 1 over x squared. So this guy, he looks different. He looks strange, but really, if we know what the y is as a function of x and we plug it in, we would get the same answer all the time that we would have gotten if we were able to avoid implicit differentiation. So yeah, don't worry. So don't worry. The implicit answer is correct. Even though it may have the dependent variable in it. So at this point, you might be wondering, well, is this thing optional then? Like, what was the big deal? Like, why did I have to go through all this trouble up here telling you about implicit differentiation? Like, I didn't need it here. Like, I could have solved for the y. It's even shorter on doing this, like not doing implicit differentiation. Like, why are you telling me about this, Jhevon? Okay, so you may think, why implicit differentiation if I could do without it? You're just pulling one of those things that math people always do, just make everything complicated. See this. Okay, so if you look at this one, same problem. We want to find y prime. Now this one is a little bit different from the last one. The last one, it was like obvious how to find y. I would say in this case that it is also still fairly obvious to find y. But it might take you a minute, especially if your algebra isn't up to snuff. So turns out we can solve for y here relatively easy. So if we wanted to do this explicitly, you would try to solve for y. What would that look like? So notice here what we have. I'm going to rewrite this very suggestively. We have x to the 4th y squared plus 5x squared plus 2x y minus 4x cubed equals 0. Hey, I brought that to the one side and I put the y squared in front. Does anyone see how to solve this or what that is? So the idea here is that this is a quadratic. It's quadratic in y. So we have ay squared plus by plus c equals 0, where a equals x to the fourth, b equals, and I mean, I could divide through by y here, but by x here, but right, could divide through by x. I'm being lazy. I just want to get to the y. So here we can apply the quadratic formula. So this means that I could solve for y equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that's your y. Now we find y prime. To which I say, nah, we ain't doing that. No, like, look at that thing. Like, why would you want to find y prime from that? That's crazy. That's actually not, that doesn't seem like it's going to be a fun thing at all. Yeah, no, we're not going to do that. So hell nah, right? So technically we could do this in the explicit way, but we don't want to. So let's not do this. So let's not do that. This guy. So here, let's go the implicit way. It's this guy. All right, so we have that. Now we know how to do this implicitly. You just go through, you differentiate both sides, and whenever you differentiate an x term, don't do anything. Whenever you differentiate a y term, multiply by y prime. At the end of the day, you're going to have a bunch of y primes. You just need to isolate them on one side of the equation, algebra. So you just solve for the y prime once you actually go through and differentiate everyone, right? That's the idea. So that's implicit differentiation. That's how it's done. Differentiate both sides of the equation, isolate your y prime in the end. So we're just going to go through and we're going to do that. In the first case here, we have this times that, product rule. We're going to differentiate the first function, leave the second, plus leave the first function, differentiate the second, which is 1, but then I multiply by a y prime because chain rule, and that's how implicit differentiation works. So here, that's product rule. Similarly here, I have one thing times another thing. And so I'm going to do the same thing. Differentiate the first function, leave the second, plus leave the first function, differentiate the second, but I have to multiply by y prime. So this is again the product rule. I just want you to pay attention to the fact that every time I differentiated a y term, I multiplied by y prime. Right? So I want you to notice that that's what I'm doing, right? So I go through and I differentiate as usual. Like I apply all the rules that we've learned so far. I apply the product rule when it's appropriate. I apply the quotient rule when it's appropriate. I apply the chain rule when it's appropriate. I do everything the way that we've learned, but the only difference is now there are x's and y's mixed up. And how I account for that is just whenever I differentiate a y term, multiply by y prime. So on the other side of the equation, it's a 4x cubed. Know how to differentiate that, that's 12x squared. And so, yeah. So now we just want to isolate the y primes. Now we solve for the y primes. And that's just a matter of algebra. Pretty much leave all the terms with y primes on one side and bring all the terms that don't have y primes on the other side. So on this side, there's going to be a 12x squared, and I'm going to subtract this guy. And then I'm going to subtract this guy. Okay. So those are the two guys that are gone. Now on this side, I'm going to have y prime, but I have a common term. So here I have 5x squared plus 2x. And then over here, I have 2x to the fourth y. So here, y prime is a common term in the other two functions. I mean, technically it's another term in the other two terms. Factor it out. And now you just divide both sides by that thing. So this would mean that our y prime is 12x squared minus 10x plus 2y minus 4x cubed 4x cubed y squared all over 5x squared plus 2x plus 2x to the fourth y. And that's your y prime. Now, if you wanted to realize what doing it the explicit way would mean, imagine this thing right here plugged in here and here. And just imagine how huge that would be. That's what you would have had to figure out if you did it. You can have some appreciation of how much pain that it would take to actually get to that answer. Yeah, doing this directly is not going to be fun. So even when we're doing it implicitly, the answer is pretty complicated, pretty big. So you wouldn't want to do it directly. So, right? So, yeah. So that's the answer. And again, there are y's in the answer, but that's not wrong. There's nothing wrong with that. If we were to rewrite the y's in terms of x's, it would be the right answer. And we can trust that because we know we can trust the chain rule, and the chain rule is what says we can do this. So yeah. So now at this point, you might be thinking, so you may be thinking, so implicit differentiation isn't necessary, but can be useful, nicer. And that's still not the full answer. So I want you to see this. Our next example. So now this guy is another example. It doesn't actually look quite as intimidating as this one here. So it's another example, and it looks nicer. So you might think, okay, what would it look like to do this explicitly? We would need to solve for y. Right? And so now you would say, well, how would you solve for y? It's x squared plus y to the 7th minus 2y equals 3. So you might think, okay, just think of this as like I'm solving a polynomial with y is the variable. Try some like rational roots theorem, maybe try to look up some formula to help you out. And it turns out that all of those things would be fruitless pursuits, because in this case, actually, it is impossible to solve for y. And I want you to appreciate that I'm not being dramatic, or I'm not trying to say, oh, it's very super hard to solve for y, and it's just because we're in Calc 1, we're not going to solve for y. No, I literally mean it is impossible to solve for y. Like, no one can solve for y. Like, it is literally impossible. You can actually prove it's impossible to solve for y in this case, which a young man did couple centuries ago, by the name of Galois. He pretty much proved that there is no formula to solve a general polynomial equation if it has power 5 or higher. So you know, like how we have the quadratic equation, there's actually an equation for cubics as well. So there's a general cubic equation, and then there's a general quartic equation, something to a 4th power, where you can, but those formulas are a lot uglier, right? They're much bigger than the quadratic formula. But there are formulas that exist that you can solve any cubic with it. You can solve any quadratic, any quartic with it. So any linear polynomial we can solve. That's not bad. Any quadratic we can solve with a quadratic formula. There's a formula for to solve any cubic. There's a formula to solve any 4th degree, but there's no formula for a 5th degree or higher. It's not that you can't solve all of these, but there's just no general formula. You might get lucky, you might not be lucky. So yeah, this is one of the ones where we're not lucky. You can actually find a formula for y here. And it's literally impossible to do so. And the story behind Galois and how we actually came to this is quite interesting. But I don't know. Maybe I'll tell you guys some other time. For now, let's just actually get through some problems. So Galois was a very young man when he proved all this, and we're still using his stuff today. And in fact, by the time you get to a point where you're actually studying the math that this kid came up with, you're already like deep into being a math major. Maybe even the first time you encounter it might be if you're doing your master's in mathematics. But undergrads can encounter it in a class called abstract algebra. And you might talk about this at the end of the first semester, but chances are you'd probably have to do 2 semesters of abstract algebra to actually even see this. So yeah, it's not simple stuff at all. But yeah, it's actually impossible to solve for y here. You cannot write this down as a formula in anything that we can understand in terms of the elementary functions that we've spoken about. So yeah, so it turns out there is no choice here. Like implicit differentiation is the only game in town. Right? Another new opportunity for this is the way, but yeah. Yeah, so it's not like, oh, I don't need to use implicit differentiation, or it's not like, well, it would be nice to use it, but it would be annoying not to, so I might just use it. But no, like all of those are incorrect. Like there are instances where you have to use it. Like there's nothing else. Like you need to know how to do this. And so, yeah, there are times when you cannot isolate the dependent variable. And so if you want to find y prime, implicit differentiation is how you're going to have to do it. There is no other way. So let's actually just do that. So remember how that works. We're going to go through, we're going to differentiate as usual, but whenever I differentiate a y term, multiply by y prime. So now I'm going to bring everything that does not have a y prime to the other side. Everything that does have a y prime stays over here. I'm going to factor out the common terms. And so our y prime is equal to minus 2x over 7y to the 6 minus 2. And that's our answer. Now, you might be thinking, but notice here, there's a y in our answer. Now, before I told you, you don't have to worry about the fact that there's a y in our answer, but this situation kind of feels a little different because you just told me that we have no idea to figure out what y is at all. Like we don't even know what it is, right? Like we don't know what it is, but it's in the answer though. Like, how is this useful? Like you just told me we don't know. If we don't know y, then we don't know y to the 6th. Because if we knew what y to the 6th was, we would just take the 6th root and find what y is. But we don't know what y is. You told me it's impossible to solve for y. So you might think, is this answer even useful? And it turns out that the answer is, of course, yes, it's useful, yes, right? Like why would I like give you something? So to kind of show you that it is useful, let me ask a follow-up question here. Find the equation of the tangent line to the curve described by this guy, x squared plus y to the 7th minus 2y equals 3. At the point, I want to say 2, 1. Is 2, 1 going to work? 2 before, yeah, 2, 1 works. You'll notice that if x is 2, right? if we set x equals 2, y equals 1, we would get 2 squared plus 1 to the 7th minus 2 times 1. This would be 4 plus 1 minus 2, and that would be 3. So 2 comma 1 is on this curve. Right, so that point does exist on the function. So it turns out that there are times when we don't know what a function is, but we can still find coordinates on that function, or we can still approximate coordinates on that function to a relatively high degree of accuracy. So even though we don't know what y is, like we can't write down a formula for it, we can kind of know what it is point by point. And that actually gives us a lot of power. And as I mentioned last time, when it comes to approximating things like that, that's the study of another field of mathematics called numerical analysis, where you kind of study approximations to equations that you can't really solve outright. So yeah, so there are times when I have a function, I can't really know what it is, I don't have a nice way to express it, but I can literally find any coordinate along it that I want. Like if I want to know, well, if my input is this, what is my output? Like I would have ways of figuring that out. And it might be difficult even though there are methods, but it's doable usually. Most of the time we want to be able to do this, we can do it with a little bit of effort. And usually with computers helping us, but it's doable, right? So I don't know what y is, but I can know that this coordinate is on that curve. Whatever y describes, it's on it. So now, by the way, this curve is, it's actually famous. It is called the Folium of Descartes. That's a very weird U, very fancy U, but I guess it was okay to be fancy there. So Descartes, the same guy who's like, I think, therefore I am. That guy, that Descartes, turns out he was also kind of like an amateur mathematician. This is the guy, by the way, a lot of people don't know this. This is the guy who invented the XY plane. Like before Descartes, there was no XY plane. We didn't know how to draw pictures of stuff, of equations. So, right. So like this is, to me, it's right up there with like the invention of zero or something. Like it really pushed mathematics forward where we're like, what, you mean y equals x squared has a picture? Like, you know, you never really thought about it before this guy. So yeah, the fact that we can have graphs and stuff, and we can have pictures of equations, and we can do stuff with pictures in math, it's like, it's a large part of it comes from Descartes. But yeah, it's actually a very famous curve. So x squared plus y to the 7th minus 2y equals 3 was a curve that this dude was studying. And its graph, when you see its graph, you're going to realize why it was hard to actually even solve for y. So it looks like this. It's symmetric, but clearly it's not a function, right? Because it doesn't pass the vertical line test. So this thing isn't even a function. So for you to write it as y equals f of x, where f of x represents a function, it's literally impossible to even do it that way in the first place. So whatever this thing describes, it would have to break it up into like 4 or 5 different parts to even start to make sense in terms of a function. You'd have to break it up. So about 6 different parts. So yeah, but this is the Folium of Descartes. So now we can't really write this down as y equals f of x, but I can know what coordinates are on it, and I can know what the derivative is. And so you might say, well, how would that be useful? So this question is going to help us see how it would be useful. Find the equation of a tangent line to this curve at this point. So now, how do we do that? Tangent line at 2, 1. So first of all, the point is 2, 1, right? That's like your x1, y1. Now the slope, that's m. But what is m? Remember, m is the derivative evaluated at the point. So here, this is just y prime evaluated at 2, 1. So that's going to be this guy, minus 2x minus 2 times x over 7 times y to the 6 minus 2. It's minus 2. Minus 2. Right, so that's actually minus 4/5. So that's the slope of the tangent line, and I know a point. So this means the tangent line is, well, y minus y1 equals m, x minus x1. So if I took the Folium of Descartes, this guy here, and someone told me, oh, they gave me the coordinate, boom, like 2, 1, then the tangent line at 2, 1 would be y minus 1 equals minus 4 over 5 x minus 2. And we can find a tangent line. Now you might say, okay, whoop-de-doo, we can find a tangent line, right? But remember what that actually means to find a tangent line. How did we get the tangent line? Well, we zoomed into the function and the function started to flatten out and it started to behave like some line that we call the tangent line. So what this basically means, we can approximate the function near 2, 1. So the idea is, I don't know what the function is, like y equals blah, like I don't know what that is. However, if I were to zoom in close to 2, 1, then whatever that formula is, it is going to behave very close to that formula, right? So near 2, 1, the y will behave like, y equals minus 4/5 x minus 2 plus 1, right? Which is a line, which is a very simple thing to deal with. Like I can know about the function by knowing about the tangent line to the function. Because if someone is saying, well, what is the function doing here? Well, I don't know exactly, but whatever it's doing, it's super close to whatever that's doing. I can know that it's decreasing. I could know that how much it's decreasing, how it's slanted. I can know a lot of information from this equation. The equation of a line is we understand equations like that very well. And so this gives you one of the side benefits of finding a derivative that I mentioned, that we get some side benefits from being able to do this. So yes, we set out to solve the rate problem, but it turns out to solve the rate problem, we had to construct a tangent line. But being able to construct a tangent line is itself valuable for reasons other than figuring out how fast something is changing. It can also help us approximate that thing. And so when something is very complicated, we can use calculus to make it a little nicer. We can actually input a function that would represent this complicated function that we don't know how to deal with, but we can make it essentially behave like a straight line in a very small window. And yes, that only works in this small window when I'm close to that point. Someone might say, well, what if I care about over here? Well, you could do the same thing. You could figure out what this coordinate is using some numerical analysis. Then you can get a tangent line at that point, and then you can talk about the function at that point. And you can literally do this at any point in the function, right? So you can do that, and you can now know how to talk about functions that were before very complicated to understand, very hard to get a grasp on, but being able to construct a tangent line is useful. So even though we don't know what the function is, being able to find the derivative is still super useful because we can use that to construct a tangent line with a little extra work, but it's doable. And it's better than not being able to do anything. It's better than just throwing up your hands and being like, well, it's impossible for us to know what's going on here, so I guess we can all go home. No, it might be very important for you to understand what that function means. It might be a life or death situation that you find the solution to that function, right? And yeah, numerical analysis and calculus can help you. Let's continue. So I think those are all the side discussions we're gonna have. I think I'm gonna just like do the rest of these like very straightforward. We kind of know the process at this point of how to find the derivative. You differentiate both sides. When you're differentiating the independent variable, don't do anything. When you're differentiating a dependent variable or any other variable other than the independent variable, you multiply by the prime. Some people like multiplying by dy dx, but it's not strictly speaking necessary in Calc 1. Because you're usually, you know who the independent variable is. Everyone else, it's kind of obvious. In higher mathematics, it's not. You can have several independent variables. So we're going to go through, do the same thing. Differentiate each term. 4x squared, derivative is 8x. 2xy, what is the derivative? You might think 2 times 1 times y prime, but you'd be making a rookie mistake by doing that. But I see it all the time because you need the product rule here. Students always forget you need the product rule. Differentiate one function, leave the second, plus you leave the first function, differentiate the second. Product rule. Same thing here for the 3x squared y squared, right? With the negative sign in front, so it's going to distribute. So instead of the product rule with a plus sign, you're going to have a negative sign because the negative sign is in front, and that would be in parentheses. So you would have differentiate the first function, leave the second, minus in this case because it's going to distribute. You leave the first function, differentiate the second, 2y y prime, because I just differentiated a y. Derivative of 4 is 0, derivative of 7 is 0, derivative of minus ln x is minus 1 over x. So that's it, the calculus is done. Now it's a matter of algebra. On this side, the y primes, the first one is attached to 2x. And that's this guy. The next one is attached to 6x squared y, in fact, minus 6x squared y. And that's done. And everyone else, I'm going to move to the other side. So I have minus 1 over x. Let's move this guy first. So over there, it becomes a positive 6xy squared minus 1 over x minus 8x, which is this guy, minus 2y, which is that guy. Everyone's accounted for. So now my y prime is going to be 6xy squared minus 1 over x minus 8x minus 2y over 2x minus 6x squared y. So that's your answer. However, you could actually rewrite this nicer, multiply by x over x to get rid of that guy, because that's kind of weird. So we get 6x squared y minus 1 minus 8x squared minus 2xy over 2x squared minus 6x cubed y. That's a little bit nicer. But that would be your answer. Same thing here. Gonna go through, differentiate both sides. All derivative rules apply. So we're just going to do the rules the same way, just that if we're differentiating a y, multiply by y prime. So how do you differentiate e to something? It's the derivative of the power times the original function. What's the derivative of the power? Well, derivative of x is 1. Derivative of y squared is 2y prime. Plus, for logarithms, how do you differentiate ln of u? It's u prime over u. So it's going to be over u, and the top has the prime, which is 1 plus y prime. Derivative of 3 is 0. So that's the calculus part done. Now we need to solve for y prime. But the y prime is kind of stuck in parentheses, so let's get it out. So I'm going to distribute this guy and break this guy up. So here I would have e to the x plus y squared plus 2y e to the x plus y squared y prime plus 1 over x plus y prime over x plus y equals 0. So here are the two guys with our y primes in it. You're going to leave them on one side. 2y e to the x plus y squared plus 1 over x plus y equals, move all the other guys over. So it's going to be minus e to the x plus y squared minus 1 over x plus y. And to make this look a little nicer, I can multiply by x plus y over x plus y. So it's minus x plus y e to the x plus y squared minus 1 over 2 x plus y e to the x plus y squared plus 1. And so that's that one. Just keep going. So here, I want to find dv dt. Notice that this is telling us p is the independent variable. V is the dependent variable. And there is another story behind this one, because this might seem like a very random thing, like 0.03 and a 9.7. Like why would you choose those numbers? Why didn't you pick some whole numbers, Jhevon? You're trying to mess with us? Well, no, this equation is actually a thing. It's actually an equation from chemistry. This is van der Waals equation. For a specific guess. And the point of this example was just that I want to show you that like implicitly defined functions where your independent and dependent variables are mixed together, it's not just something that math people make up just to have a reason to do this new type of differentiation. Like, let's just make this up, like create a problem and solve it. But these things actually occur in real life. Like you're studying science or you're studying something else in the real world. There are times when the things you're studying and you're trying to find a relationship between them, this is how you discover the relationship. They're kind of mingled together. And so you might still want to be able to examine this relationship using calculus. So this is an example to kind of show where that's coming from. So here's van der Waals equation, where P stands for pressure and V stands for the volume of a specific gas. It turns out that this is the relationship between them. But what if I want to know how the volume will change with respect to pressure? Like if pressure increases by 1 atmosphere, what happens to the volume? Pressure decreases by 1 atmosphere, what happens to the volume? You might want to know those things. Or if my pressure is increasing at this rate, what's going to happen to my volume? Is it going to get smaller at what rate? Or if my pressure is decreasing at this rate, how fast will my volume change, right? Is this thing going to be an explosion or is it not, right? These are things you might want to know. But yeah, calculus can help us answer these questions. So I'm going to go through, going to differentiate. So I might rewrite this here because it's might look a little strange. We have P plus 5V to the minus 2 and V minus 0.03 equals 9.7. I want to find dV dP, which means that if I differentiate a P, I don't have to do anything. If I differentiate a V, I have to multiply by V prime. So I'm going to differentiate the first one. V prime, leave the second, plus leave the first, differentiate the second. What's that? So now my V prime, this is the dV dP, right? Just like how Y prime was the dy dx. And here I would have, now I want to solve for the V prime. So I would just actually multiply out. So I'm going to multiply 1 times this, 1 times that, then this times that, this times that. So that's going to be V minus 0.03 minus 10V to the minus 2 V prime plus 0.3 V to the minus 3 V prime plus P plus 5V to the minus 2 V prime equals 0. So now this guy has my V prime, that guy has a V prime, this guy has a V prime. I'm going to move the other guys to the other side. So it's 0.03 minus V. And over here, I'm going to have V prime times minus 10V to the minus 2 plus 0.3V to the minus 3 plus P plus 5V to the minus 2. Kind of got very sloppy right now. 5V to the minus 2. Which these guys can combine. I think these two here can combine. That's minus 5V to the minus 2. So and there's your V prime. That's your dV dP. last example. Yes. I mean, I wanted to get a little farther, but it's 9. So hopefully that was okay, understandable. So the main takeaway is implicit differentiation. It's necessary sometimes. You do it when your dependent variable and independent variable are mixed together. And essentially you obey all calculus rules. You go through and differentiate both sides. Whenever you differentiate an independent variable, don't do anything extra. When you differentiate a dependent variable, multiply by y prime, because the chain rule will take effect. And then at the end of the day, solve for the prime. It's not necessarily y prime, because here you see we had v prime or whatever. But the idea is you multiply by the prime of the dependent variable. We saw how tangent lines can be useful, and we did some more derivative examples. Okay, so I think that's enough. So your test is going to be, like I said, just like what was on the practice exams. So it'll go up to implicit differentiation, and it will have some bonus problems on the next couple sections. So if amazingly you have extra time after studying, you can look up things like log differentiation. And I think the next thing I'm going to do is L'Hopital's rule and indeterminate forms, and then some like related rates. Thing is that sort. I think the practice exam would have the type of bonus problems that I would ask. So you can even do some of those. But for now, we'll stop there. Hopefully that was okay. Thank you for your time and attention. I will let you guys go. Good luck, and see you guys in the next one.